All right, this is our very last concept in this unit, and we're going to be focusing on how to write an equilibrium constant and what it means. Now, when a system reaches equilibrium, it's important to know the relative amounts of the products and reactants. And the equilibrium constant, which you're going to see is KEQ, that's what that represents, is going to give us that information about do we have more reactants than products, or more products than reactants, or are they equal? Now, this only involves gases and mixtures. We never can involve liquids or solids. And also, the only way to change this number, this constant, is to change the temperature. Now, for simple systems, it's just simply the concentration of the products over the concentration of the reactants. That's what these brackets mean here, is concentration. Now, you need to know and memorize this information over here. If your equilibrium constant is greater than 1, that means you have more products than reactants, and that should make sense. You have a larger divided by a smaller number. If it's less than 1, then you have less products than reactants, which again should make sense because you have a smaller divided by a larger number. And if the equilibrium constant is equal to 1, that means you have the same amount. Now, not every system is going to look like this. It's still that the concentration of the products divided by the reactants, but we're going to be raising each of the concentrations to the power of its coefficient. Now, here we have an example, and each of the lowercase letters represents a number, and the capital letters are representing an element or a compound. So as you can see, P and Q are our products. So we have those in our brackets representing their concentrations, and each one is raised to the power of its coefficient, which again, each of these would actually be a number from either 1 and up. So we have P raised to C, so say it was 2P, it would be P squared. And then that's divided by the reactants, M and N, and each of those are raised to its power. So this will make a little bit more sense when we actually work with some full equations with actual numbers, just so you can see how this plays out. Now we have a little visitor to help us go over this little piece of information.
Only a change in temperature will affect the value of the equilibrium constant. Changes in concentration or the addition of catalyst will not cause a change in the value of the equilibrium constant.
Alright, so again, temperature is the only thing that can affect this. Catalysts or changing the concentration will not change the actual value of the equilibrium constant. Alright, and then finally the solubility product constant. This just is a special type of equilibrium constant because it measures the concentration of ionic compounds in water. So it really helps you to tell how soluble a compound is. If the KSB is small, then it's only slightly soluble. If the KSB is large, then it's considered very soluble. And let's see how to write one of these. So here we have our dissociation of this ionic compound. Remember, AQ is showing that they're mixed into water and they're ions, so they've been broken apart. Remember, products over reactants. However, remember we said in the beginning there can be no solids involved. So we need to get rid of AB, and that means that the KSB, or the solubility product constant, is the concentration of the two ionic compounds. All right, well that is it, and we'll start practicing this tomorrow in class.